So we were talking about the density property. That means here we are choosing 1 by nth interval of the rational point C. Then there will be infinitely many irrationals. We are naming that irrationals as xn. So then xn minus C will be less than n. So from this line what we can write as n tending to infinity, the sequence xn is tending to C, right? Because if you apply n tending to infinity on both sides, this quantity will tend to 0. That means xn minus C is tending to 0, that is xn tending to C. Now tell me, what is the value of f of xn? What? Minus 1. Yes, because xn is an irrational number. So f of xn is minus 1. So xn is tending to C, but f of xn is tending to minus 1, which is obviously not equal to fc, because we have already calculated the value of fc, which was 1. So this is by using sequential criteria, we can say the function f is not continuous at the point C. So by sequential criteria, the function is not continuous at x equals C. Okay, this is for the rational part. Now we have to prove it, the same thing for the irrational part. Okay, now anyone tell me how to do the next part? What will be the first line for any rational point? The same thing. Let's take D. We have already taken C, so let's take D. Let D be any irrational point. Okay, then what will be f of D? Minus 1, correct. Now by density property, what will you write? Exactly, infinitely many rational points yn, taking the points as yn, such that what will be the range? D less than y. Yes, yn minus D less than 1 by n, right? Like this is our D in real line. We are considering this interval. This is D plus 1 by n. This is D minus 1 by n. So obviously by density property, in that area or in that region, there will be infinitely many rationals as well as irrationals. We are choosing the rationals only, naming it as yn, y1, y2 and so on. Okay, so yn minus n is less than 1 by n. So from there what we can conclude about the sequence yn? What we can conclude about yn? About the convergence of yn? Yn is tending to D, because if you take n tending to infinity on both sides, this part will tend to 0 as n tending to infinity. That means yn is tending to d. So in the next line we are writing tending to d. Now what about f of yn? What will be the value of f of yn? 1, because yn is a rational number, so this is equals 1. Is it equal to fd or not? No, because fd is take the value minus 1, so this is not equal to fd. So we got one sequence yn which is tending to d, but f of yn is not tending to fd. That means the function is not continuous at the point d. So by sequential criteria, f is not continuous at x equals d. Okay, so f is not continuous at rationals and not continuous at irrationals. That means f is not continuous at any real number. Okay, so this is how we use sequential criteria to disprove something, and this type of examples are very important for exam. We will solve few more examples. Write down next one. Prove that fx equals x when x belongs to q and minus x when x does not belongs to q is continuous only at x equals to 0. Now for such type of examples there is a trick, okay, how to find that where the such type of functions will be continuous. Just you have to make sure this and this are equal at that point, then this point will be the point of continuity. Okay, so here if you equate in rough, obviously if you equate x equals minus x, what will you get? What will be the value of x? The value will be 0, so the function will be continuous only at x equal to 0. This is not the actual procedure, okay, this is a back procedure to check, but we have to prove it. But suppose question comes like, find out the point where the function is continuous, then in the back process you can use this procedure to get which point will be the point of continuity. Okay, now here it is given that you have to prove at x equal to 0. So at first we will prove that it is continuous only at x equal to 0. Then we have to prove it is discontinuous in any other point. So for the continuity part, someone tell me how to do that. Obviously using epsilon delta concept. How to solve it? By using epsilon delta concept. Starting with fx minus fc, what is the value of c here? 0. So fx takes the value something at irrational, something at rational. So using this bracket, this will be x minus 0 when x belongs to q, right? And minus x minus 0. F0 is obviously 0. If you put, then you will get it. This x does not belongs to q. So this is mod x and this is mod of minus x. Now mod of minus x and mod of x, both are same. That is ultimately it will become mod of x for all x belongs to R. Right? Now how will you do that? The next step is very easy, just to find the value of delta. We can write it like this. Then it will be x minus c, right? So what will be the value of our delta? X. No. How will delta be x? Epsilon. Yes, delta will be epsilon because this is x minus 0 or x minus c, which is less than delta, right? And if you choose delta equals epsilon, then x minus c is less than delta. This is satisfied. And fx minus fc is less than epsilon. This is also satisfied. So delta will be equal to epsilon. So for this delta, we can claim the function is continuous at x equal to 0. Now we have to prove for another points. Exactly the same procedure like the previous problem. So at first, for the rational cases, we are choosing any arbitrary rational number. Let c be any arbitrary rational number with c not equal to 0, because we have already discussed the case when the point is 0. We are considering only the non-zero points. So let c be any arbitrary rational number. Then tell me what will be the value of fc. C, because fx takes the value x when x belongs to q. So c be any arbitrary rational number where if fc equals c. Then the same thing by density property, there are infinitely many irrationals xn such that modulus of xn minus c is less than 1 by n, right? Now when n tending to infinity, this part will tend to 0. That means the sequence xn will tend to c. Now what about the sequence f of xn? Where will it go? Minus c, because xn is an irrational point, so this will go to minus c. Is it equal to fc? No, because fc is equals to c, that is this is not equal to fc. So we get a sequence xn which is tending to c, but f of xn is not tending to fc. So by sequential criteria, fx is not continuous at x equal to c. Okay, this is for rational numbers. Now we have to prove it for irrationals. So tell me, what will we write for the next case? No need to write d not equal to 0, because 0 is not an irrational one. We consider 0 as rational one. Okay, so let d be any arbitrary irrational number. Okay, what will be the next line? Okay, someone else tell me the next part. Okay, then then f of xn is c, actually f of yn. Okay, f of yn, that will tend to where? 0. Why? It will tend to d, yes, as n tending to infinity, which is not equal to fd, because we have checked fd is equals to minus d. So by sequential criteria, fx is not continuous at x equals to d. Okay, that means it is not continuous at any non-zero real number. It is only continuous at x equal to 0. So this is how we solve such type of problems. Now I am giving you few homework. Okay, write down next one. Test the continuity of fx equals x when x belongs to q and 1 minus x when x does not belongs to q. Test the continuity of fx when fx equals this. Now can anyone tell me what will be the point of continuity for this function? Is there, if any? Half. Yes. Yes, correct. Just by equating this and this. So at first you have to prove that the function is continuous at x equal to half. Okay. Then you have to take one rational c not equal to half. Then you have to prove it is not continuous at x equal to c. Then you have to take another irrational d. Then you have to prove that this is also not continuous at x equal to d. Okay. This is the whole procedure. This is your homework. Next, write down another one. Test the continuity of fx equals x when x belongs to q and 0 when x does not belongs to q. This one. Next topic is algebra of continuity. That means whenever two function f and g is continuous at some point x equals c, then f plus g, comma f minus g, comma f into g, comma 1 by f, comma f by g, comma mod f, these are all continuous at x equal to c. Okay, provided f not equal to 0, g not equal to 0, because otherwise it will be undefined. So whenever f and g are continuous at x equal to c, these functions, all functions will be also continuous at x equal to c. Okay, we have to prove this. So 1, 2, 3, 4, 5, 6, total 6 proofs are there. I'll do few of them, the rest of will be your homework. Okay, the proofs will be exactly same like that limit chapter, exactly same proof. Just instead of L you have to use FC. So starting with the easier one, f plus g. Okay, So we have to prove that a plus g is continuous at x equal to c. So we have to prove a plus gx minus a plus gc. This quantity will be less than epsilon, right? So let us expand it. Fx and fc, writing it together, and gx and gc, writing this together. Now applying this and this over these two, applying triangle inequality. So we can write this quantity is less or equal to this plus this. Okay, this is number 1, equation number 1. Now we have in our hand two given conditions. F is continuous at C and G is continuous at C. So we are applying for this continuity part, we are applying the epsilon delta definition. So what we can write, for given epsilon greater than 0, there exists a delta. Now we need more than one delta. So for that reason we are naming it as delta 1. Okay. So there exists one delta 1 greater than 0 such that modulus of fx minus fc is less than epsilon when x minus c is less than delta 1, right? This is the definition. Now by checking equation number 1, from equation number 1, what we are trying to prove? We are trying to prove this quantity is less than epsilon, right? This is our main target. So we have to prove that this whole quantity will be less than epsilon. Okay. Now check equation number 1 and check this line. So what we will write in that position instead of epsilon, so that we can get equation number 1 is less than epsilon. Yes, epsilon by 2. If we write here epsilon by 2, in the next step we will also take for this part epsilon by 2. Ultimately epsilon by 2 plus epsilon by 2 will give the result epsilon, right? So this one, this is 2. Again G is also continuous at C. So for same epsilon greater than 0, there exists a delta 2 greater than 0 such that modulus of Gx minus Gc will be less than epsilon by 2 when x minus c is less than delta by 2, right? This is equation number 3. So what will be our next line? 2 is true for this range, for this delta 1, and 3 is true for this range, for delta 2. So what will be our new delta? Yes. So let's take let delta equals minimum of delta 1 comma delta 2, because delta 1 delta 2 both are the length of an interval. So we are choosing the minimum one where both the inequality holds. So this is why we are choosing minimum of delta 1 and delta 2. So for delta equals this, then for x minus c less than delta, we have 2 and 3 both holds. So we are putting 2 and 3 in equation number 1. That means f plus gx minus f plus gc less than epsilon by 2 plus epsilon by 2 equals epsilon. Okay. So this proves that the function f plus g is continuous at x equals c. This proves the theorem. Now the converse of above theorem is obviously not true. Can anyone give me one example about the converse? That means sum of two functions are continuous, but the functions are individually not continuous. Exactly the same example we have taken for limit will work here. Yes, Dirichlet function. So tell me what will be f and what will be g? Q. Minus 1 when it belongs to Q. Okay. And G? And 1 when x doesn't belongs to Q. Yes. So what will be f plus g? 0, always 0 if you take any rational point or irrational point. Yes, 0 for all x belongs to R, which is a constant function, and we know constant function is always continuous. So f plus g is continuous, but individually not fx, not gx. No one is continuous. We just prove it. That is, this function is not continuous. Okay. So this is the counter example. That's it for today. In the next class, we will prove one more theorem of this algebra of continuity part, and then we will start up to the boundedness part. Okay. And next class will be on this time tomorrow, 3 p.m.